Let's start your Calculus 2 course with a quick review of the two main ideas in Calculus 1, the derivative and the... So first of all, we'll talk about something called an average rate of change. The average rate of change of a function over a time interval is the change in the y values of this function divided by the change in the x values, usually denoted by delta y over delta x. What would the average rate of change mean in the following context? So suppose we have a function. So here's our function. And we have 2 points in that function. The first point right there, that's x1, y1. The second point right there, x2, y2. Okay, so delta y over delta x will equal y2 minus y1, that's the change in the y values, divided by x2 minus x1. And that should look awfully familiar. You've seen that a gazillion times since Algebra 1. That is the slope of what's called the secant line. And that secant line is the line going through those 2 points. All right, next, suppose we have a position function. Let's just call it y equals f of x, where x is equal to your time, and it's measured in, we'll say, seconds, and we'll let y equal your position measured in feet. In this case, delta y over delta x will be your change in position divided by the change in time. And that is going to give you the average velocity. Right. If we have a population function, so similar to the last example, suppose once again you have something y equals f of x, where x is measured in years, and we'll say y is in the number of moose. In this case, delta y over delta x is the change in moose per year, so the average rate of growth of this population. Average rate of growth in moose per year. Now, how that relates to the calculus is something called the... So the derivative is the instantaneous rate of change of a function at values in the function's domain. The derivative is defined as the limit of the average rate of change of the function. So first we're going to get the limit definition, and we're going to describe what the derivative would signify in the following situations. So first of all, the limit definition of the derivative is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And this will give the slope of the tangent line at a particular value for x. Another way to define this is f prime of a, where a is a particular x value, is equal to the limit as x goes to a, f of x minus f of a over x minus a. And the second one is a little easier to see how that relates to that whole average rate of change business. F of x minus f of a, that's delta y. X minus a, that's delta x. And the whole x going to a part, that means that the distance between the delta x is getting smaller and smaller and smaller because x and a are getting closer and closer together. Situations, If you have the graph of a function, now this derivative is the slope of the tangent line. And the tangent line is a line that passes through that function and has the same general direction and shape as the function at that particular point. If you have a position function, this is going to give you the velocity at a particular time. And if you have a population function, it will give you the instantaneous rate of growth. Of that population. So now the next thing is just something you have to remember from calculus. We have a whole bunch of rules for finding derivatives that all come from that limit definition, but you just have to know these. So we'll review them really quickly, and if there are rules you do not remember, let me know or talk to me in the math lab and get some help with this. So the derivative of x to the power of n, where n is some number, is n x to the n minus 1. It's called the power rule. E to the x is everybody's favorite. The derivative of e to the x is itself, just e to the x. Sine's derivative is cosine. Cosine's derivative is negative sine. The derivative of tangent is secant squared x. Secant x's derivative is secant x tan x. Cosecant's derivative is negative cosecant x cotangent x. Cotangent's derivative is negative cosecant squared x. The derivative of natural log of x is 1 over x. A to the x students often have trouble with. It's kind of similar to e to the x, just a little different. You have ln of a times a to the x. And that rule will still work if you have e to the x, because ln of e is just 1 times e to the x, so same thing. All right, log base a is also somewhat similar to ln. That derivative is 1 over ln a times x. All right, lastly, the inverse trig functions. Arcsine's derivative is 1 over the root 1 minus x squared. Arccosine's awfully similar, just it's negative, negative 1 over the root 1 minus x squared. And arctangent's derivative is 1 over 1 plus x squared. Next, we have combined functions of the previous type by multiplying them by constants, adding them together, multiplying two functions by one another, taking the quotient, and composing functions. So if you have a constant times a function, you want to find the derivative of that. What you have, the rule there is this derivative is just the constant times the function's derivative. So constants can factor out of differentiation. If you have a sum or difference and you're finding the derivative of a sum or difference, you just add or subtract these derivatives of each individual term. So that's f prime of x plus or minus g prime of x. Now, for the products and quotients and compositions, things are a little bit more tricky. The first one, we use something called the product rule. So the derivative of f times g is f prime of x times g of x. Notice that's not differentiated. Plus f of x times g prime of x. You only differentiate one function at a time. Now the derivative of a quotient is given by the following. It's g of x times f prime minus f of x, g prime of x, all over g of x squared. I remember that one like this. Low d high minus high d low, all over low squared. So what that means is the bottom function is the lower function, the top function is the high function. Low derivative of the upper function minus the high derivative of the lower function. I'm forgetful. That helps me remember it. The last one, this one is called the chain rule. So you have g of x inside of f. So first you differentiate f, and g does not change. And then you multiply by the derivative of the inner function. All right, next, let's apply some of these rules. Okay, so first I have f of x is cosine x minus 5. This one's a pretty simple one. The derivative here, you can just differentiate each component individually. Cosine's derivative is negative sine x. Negative 5 is a constant. Its derivative is 0, so that's negative sine x minus 0, or f prime of x is just equal to negative sine x. All right, simple power rule application. F prime of x, the derivative of 5x is just 5. On x to the fifth, we apply the power rule. We have 5x, power goes down by 1 to the fourth. All right, first we're going to use the power rule in this one, but first you have to rewrite this function f using powers with that, not rational, not roots, and not 1 over x squared needs to be rewritten. So we rewrite f of x as 3x to the negative 1/2 plus x to the negative second. Now f's derivative, notice that you have to have proper notation there. The first thing is still the original function. Now we have the derivative. So we'll have 3 times negative 1/2 x to the negative 1/2 minus 1 minus 2x to the negative 2 minus 1. So that is negative 3 over 2 x to the negative 3 over 2 minus 2x to the negative 3. And it's best to give your final answer with negative exponents put back in denominators if they need to be. So negative 3 over 2x to the 3/2 minus 2 over x cubed. And that's your derivative. Technically speaking, just so you know, x to the 3/2 could also be written as the square root of x cubed. The denominator is the kind of root, in this case a square root. The numerator is the whole number power. All right, this is the first one that has an example where we're using one of those rules. This one is going to use the chain rule. So first of all, f of x is equal to 2x plus 7 to the power of 1/2. So our outer function is this power of 1/2. So we apply the power rule. F prime of x will equal 1/2 times 2x plus 7 to the 1/2 minus 1. So notice the 2x plus 7 did not change. Now the chain rule says multiply by the derivative of that inner function. Now the derivative of 2x plus 7, let's write that down, derivative of 2x plus 7. So f prime is 1/2 2x plus 7, the quantity to the negative 1/2, multiplied by 2. And simplifying further, we get 1 over the square root of 2x plus 7. All right, secant squared x. So similar idea, just notice that secant squared is actually secant of x to the second power. So there the outer function is the squared function. So f prime of x will equal 2 secant of x to the first power multiplied by the derivative of secant x. So that's 2 secant x times secant x's derivative is secant x tan x, which we can simplify slightly into 2 secant squared x tan x. All right, let's find the derivative of this function. We have sine of 5x times e to the 3x. Now, to find the derivative of this function, we have to use two rules. We have to use the product rule and the chain rule. So the product rule says that the derivative of a product, if we have a first function and a second function, is the derivative of the first function times the second, plus the first function times the second derivative. So in practice, here's what that means. F prime of x will equal, first we differentiate sine of 5x. We have the derivative of sine 5x multiplied by e to the 3x. And then plus, in this next part, sine of 5x is left alone, and you differentiate e to the 3x. Now to differentiate sine of 5x, you need to use the chain rule. So sine 5x's derivative is cosine of 5x times 5, and then e to the 3x, plus sine 5x. E to the 3x's derivative is e to the 3x multiplied by 3. Now take out the greatest common factor, which is... Next, we're going to find the derivative of this tricky trig function, tangent x divided by secant x. So to find this derivative, we need to use the quotient rule. So g prime of x will equal low, so secant x, d high times the derivative of tangent, which is secant squared x, minus high tan x, the derivative of times the derivative of secant x, which is secant x tan x, all over secant squared x. Now you should be happy because you can use the quotient rule, good for you. Next, you should simplify this slightly if you can. So first, look for a greatest common factor. Now the numerators, both terms have secant x. Let's factor that out. We have secant of x times secant squared x minus tangent squared x over secant squared x. So we can cancel out a secant x. So we have secant squared x minus tangent squared x all over plain old secant x. And that's pretty good. You just need to remember something about secant squared x minus tangent squared x. So here's your little thought bubble. And you're thinking, I know that sine squared x plus cosine squared x equals 1 because you're all trigonometry rock stars. So if you take that identity, you divide it by cosine squared x, sine squared over cosine squared gives you tangent squared x. Cosine squared over cosine squared is equal to 1. Will equal 1 over cosine squared is secant squared x. So what this identity means is that secant squared minus tangent squared x is equal to 1. So this is actually equal to 1 over secant of x, which, one last thing, is 1 over cosine of x, which simplifies to plain old cosine of x. That last bit was a bit tricky, but you're going to need to know these identities later on in this course, so it's important to review them now. All right, now that we have talked about derivatives, we are going to move on to antiderivatives. Now, the whole reason we came up with antiderivatives is we wanted to find an area under a curve. So, and just like we began finding derivatives by finding these secant lines that estimated the tangent lines, we're going to use something called a Riemann sum to estimate an area under a curve. And this is still a very good method if you can't actually use the antidifferentiation process that you know about. So in general, a Riemann sum is an estimate, or it's a method of estimating an area of a region under a curve. So we're going to use it to estimate, it's an estimate of the area of a region under a curve. And I probably should say signed area, because in this case, if your curve goes below the x-axis, you count that area as negative. So in general, what you do is this, is you take, suppose you have your function, let's assume it's positive, and you want to find the area between those values. You divide it up into little pieces, and you pick some sample point in the middle. You could use left points, you could use right points, you could use midpoints. Let's just draw the picture with left endpoints. You go up to the curve at the left endpoint, make a rectangle. And then you know how to find areas of rectangles, and you add them all up, and that gives you an estimate of your area. So that's what a Riemann sum is in general. So Riemann sum encompasses all the different kinds: left sums, right sums, midpoints. Even the trapezoid rule is an example of a Riemann sum. So a definite integral is the limit of Riemann sums on an interval as the width of the subinterval goes to 0. So the idea is you take that picture we drew in the last slide and make the boxes get smaller and smaller and smaller and smaller widths. If the function is always non-negative on an interval, what geometric quantity does this represent? This gives you the regular old area under the curve. And if the function is not always non-negative, meaning occasionally it goes negative, this gives you the total signed area under the curve. So in that case, your negative area could cancel your positive area. So let's have a specific example to explain what that would mean. So suppose this is a velocity function. Pretend that I actually drew a symmetric picture, and this is v of t, which is measured in meters per second, and t is measured in seconds. The area under that curve will give you the meters traveled by this particle or person or object. Now, what this part means here is that initially you went backwards, and then you went forwards, the same distance, let's say. So overall, your position didn't change at all. Nothing happened to you. So in that case, this would be what's called the displacement. But the point is this is the signed area, so parts below the x-axis count as negative area. And what you learned in Calculus 1 was how to use the Fundamental Theorem of Calculus to find the area under a curve. And what that said was this, is that the integral from a to b of little lowercase f of x dx is equal to capital F of b minus capital F of a, where capital F is an antiderivative of little f, which means that capital F prime equals little f. And you also have to assume that f is continuous on the interval from a to b. In this course, we're going to learn how to deal with situations where your function is not continuous over the interval. But for right now, you assume your function is continuous. And since this process requires that you find an antiderivative, another rather large component of Calculus 1 was figuring out certain kinds of antiderivatives. So let's first review some common antiderivatives that you should know, and then we will do some examples of finding areas under curves using that technique. Right, so we're all going backwards. So the antiderivative of u to the n is 1 over n plus 1, u to the n plus 1 plus c. And for that one, we must assume that n does not equal -1. Now, the way you check this is if you differentiate this column that we're putting the antiderivatives into, you should get back what was inside the integrand. So the derivative of u to the n plus 1 times 1 over n plus 1 does give us back u to the n. So the next one, sine. So who has a derivative of sine? So is it plain old cosine? Let's try cosine u plus c. So cosine's derivative is negative sine. So if I differentiate this, I get negative sine. So in order to not have negative sine and get positive sine, I need a negative right there. Okay, the antiderivative of cosine is just plain old sine. All right, whose derivative is secant squared? Think for a second. That's right, tangent. So tangent u. Whose derivative is secant u tan u? It's just secant u. Cosecant, well, cotangent of u is almost correct. You just need a negative sign. The function that has cosecant u, cotangent u as its derivative is negative cosecant u plus c. E to the u is still your favorite. The antiderivative of e to the u is just e to the u plus c. A to the u's antiderivative is 1 over ln of a times a to the u plus c. All right, tangent's a little bit tricky, and the derivation of this is something you can reference your textbook for, but the antiderivative of tangent is the natural log of the absolute value of secant of u plus c. All right, whose function's derivative has 1 over 1 plus u squared as its derivative? That is actually arctan. You see, the next one looks awfully similar. It's just a squared instead of 1. And how you generalize that previous formula is this. The antiderivative of this function would be 1 over a arctan u over a, once again plus c. Now the next one, 1 over 1 minus u squared, the antiderivative there is arc sine. You could make arc cosine work, but usually we just say arc sine because it's simpler. And this next one is also very similar. It's just arc sine u over a plus c. And lastly, the antiderivative of 1 over u is ln absolute value of u plus c. Now we're going to use those to find some areas under curves. So unlike differentiation, antidifferentiation does not have any set rules. There are just techniques. So it often involves just being a little clever and seeing lots of different examples. All right. So find the definite integral of sine x between 0 and pi quarters. This is saying find the area under the sine curve between 0 and pi quarters. So let's just draw a little picture of what that is. So sine begins at 0, at pi over 2, sine is 1, by pi we're back down at 0. So we should get a positive number for this. So an antiderivative for sine is negative cosine of x, evaluated from 0 to pi quarters. So first you plug in pi quarters, we get negative cosine pi quarters minus negative cosine of 0. So that's negative root 2 over 2 plus 1. All right, the definite integral from 1 to 5 of x plus 1 over x. So first of all, the antiderivative of x will be 1/2 x squared. The antiderivative of 1 over x will be ln absolute value of x from 1 to 5. So first we'll plug in 5. We get 25 over 2 plus ln of 5 minus 1/2 plus ln of 1. Okay, so that's 24 over 2 plus ln of 5. ln of 1 is 0, or 12 plus ln 5. All right, this next one just involves some not very tricky, but maybe semi-tricky algebra. 1 to 4. You can make this into 2x over 2x plus 1 over 2x. Usually you do stuff in this direction. You have a common denominator, you add the numerators. We're just undoing that. Okay, now that simplifies down to 1 to 4. 1 plus 1 over 2 times 1 over x. So the antiderivative of 1 is just x. The antiderivative of 1/2 times 1 over x will be 1/2 ln absolute value of x. And once again, we'll go this time from 1 to 4. Okay, so first plugging in 4. We have 4 plus 1/2 ln of 4 minus 1 plus 1/2 ln of 1. And that will be 3 plus 1/2 ln of 4. And tricky thing with ln's is this 1/2 can pull back up and become a power. So that could also be written as 3 plus ln square root 4 or 3 plus ln of 2. Now, so far you do not know a technique to figure out this particular area under this curve, but you should be able to recognize that 36 minus x squared square rooted actually is a semicircle. And here's why. We know that x squared plus y squared equals 36 is a circle centered at the origin of radius 6. Solve that for y. Y squared is equal to 36 minus x squared. Technically, y equals plus or minus the square root, 36 minus x squared. Now, the positive root gives you the upper half of that circle. The negative root gives you the lower half of that circle. So what we have in this particular integrand is a semicircle of radius 6, so that's negative 6, that's positive 6. The fact that the integral goes from 0 to 6 means that I want the area under this curve right there. So I have a quarter circle. So this integral is the area of a quarter of the circle of radius 6. So 1/4 times pi r squared. The r is 6. 1/4 pi times 6 squared. So that's pi over 4 times 36. Or 9 pi. Now the most sophisticated technique that you have for antidifferentiation is substitution. Now this is a method to sort of make the integral look like some of the stuff you already know. Technically speaking, what you're doing here is you're undoing the chain rule. So usually you make a substitution for whatever is inside of something else. So for example, in this function we have negative 3x squared inside the e to the function. So we're going to let u equal negative 3x squared. Then you also need to replace the dx. So you take the derivative of this u, or find what's called the differential. Du will equal negative 6x dx. So this becomes the integral e to the u. Now you replace the x and the dx, so you have x dx right there, right? So dividing that by negative 6, negative 1/6 du is what replaces x dx. And this only works if you can replace everything. So negative 1/6 du. So the antiderivative of e to the u is e to the u, so we get negative 1/6 e to the u plus c, and then put back in what u was, negative 1/6 e to the negative 3x squared plus c. And you can check your answer by taking the derivative of this. You should get back what you had at the beginning. So let's just check. Negative 1/6 e to the negative 3x squared, because the chain rule will multiply by the derivative of negative 3x squared, which is negative 6x. So you have this negative 6 cancels the negative 1/6, and I get x e to the negative 3x squared, which is what I was supposed to get. Let's try another one of those. All right, in this one, you can try, the only situation I see that would work would be to let u equal the whole denominator. So let's try let u equal 1 plus cosine of x. All right, then du will equal negative sine x dx. Negative du equals sine x dx. So this then becomes negative du over u, or in other words, negative the integral 1 over u du. Now the antiderivative of 1 over u is ln, absolute value of u, plus c, and plug in what your u is, negative ln, absolute value, 1 plus cosine x, plus c. Okay, a slightly more complicated one. I have tangent to the n secant squared x. The thing you should recognize is if you u sub for tangent, its derivative, which is secant squared x, shows up there. That's what you're kind of looking for, is some function whose derivative appears in your problem, in your integrand, up to a constant. So if you let u equal tangent of x, then du is secant squared x dx. So this becomes the integral of u to the n du. And now it's just the reverse power rule. The antiderivative of u to the n is 1 over n plus 1. Whoopsies. 1 over n plus 1, u to the n plus 1 plus c. So we'll have 1 over n plus 1 tangent of x to the power of n plus 1 plus c. Once you're here, you can see the reason that you had this restriction that n could not equal negative 1, because if n could equal negative 1, this could be 0. And I have to treat that case special differently. All right. All right, here's an example of a u substitution that's a little bit tricky. So try to let u equal 2x minus 1. The derivative of u will be 2 dx. So, well, you can replace dx by 1/2 du will equal dx. Okay, now this gives you over root u, pull the 1/2 out in front, du. Now that x in the numerator, you still have to replace that. You cannot have both x's and u's all mixed up there. So what you do is this. Take the substitution that you made. You can solve that for x. U plus 1 will equal 2x, or 1/2 u plus 1 will equal x. So you see that x can be replaced by 1/2 u plus 1. So pull out that 1/2 and multiply it by the other 1/2, giving you 1/4. Integral u plus 1 over u to the 1/2 du. Divide both components of the numerator by u to the 1/2. We'll have 1/4 antiderivative u to the 1/2 plus u to the negative 1/2. And now you've reduced it to a power rule which you can antidifferentiate. So 1/4 u to the 3/2 times 2/3 plus u to the positive 1/2 times 2 plus c. I'm going to distribute my 1/4, cancel, and reinsert my u. So we'll have 1/6 2x minus 1 to the 3/2 plus 1/2 root 2x minus 1 plus c. That is your, that's the trickiest that a u substitution is going to get generally. thus far, all the examples that we've had of u substitutions have been examples where they have been indefinite integrals. This one is a definite integral with those numbers 0 and 1. So what we have to do here is you have to change your bounds. Right now, they're bounds on y. We're going to make them bounds on u instead. So start by letting u equal 1 plus y squared. Du will equal 2y dy. So 1/2 du will equal y dy. All right, so this, now the tricky thing there are a couple things that are tricky. First of all, 0 to 1. Y cubed is y squared times y. That's not very tricky. So the y gets replaced by the 1/2 du. Now that y squared, you have to say, take the substitution, you'll see that u minus 1 equals y squared. Okay, so we'll leave the bounds off for now, but we'll come back to them in a second. So the y squared is replaced by u minus 1. The y is replaced by 1/2 du, and the 1 plus y squared is replaced by u, so square root u. Okay, now, first of all, if y is equal to 0, using your substitution, translate that into a u. If y is 0, u will equal 1 plus 0 squared, or 1. And if y is equal to 1, u will equal 2. So this becomes the integral from 1 to 2. So to find the area under the y cubed times the root of 1 plus y squared curve between 0 and 1, you find the area of this other curve between 1 and 2. So we're just going to tackle this problem now. So pull out the 1/2 and have u minus 1 times u to the 1/2 du. There's no product rule for antidifferentiations here. Best bet is to simplify. Distribute that u to the 1/2 and add powers. So we have 1/2 antiderivative from 1 to 2, u to the 3/2 minus u to the 1/2. And now antidifferentiate. We'll have 1/2 times u to the 5/2 times 2/5 minus u to the 3/2 times 2/3 from 1 to 2. When you work that all out and plug everything in, you get 2 root 2 plus 7 over 15. It's a little bit tedious. The notes online have that all worked out for you if you want to check your work. So similar idea, let's try it again. So probably going to let u equal 2 plus tan x. The reason is when you find the derivative of u, you get secant squared x dx. Nice and simple. Let's change our bounds. If x is equal to 0, u is equal to 2 plus tangent of 0. Tangent of 0 is 0, so u is equal to 2. And if x is pi quarters, u is equal to 2 plus tangent of pi quarters. And tangent of pi quarters is 1, so u is equal to 3. So this integral becomes the integral from 1, oops, wrong, that's wrong, 2 to 3, 1 over square root u du, or 2 to 3 u to the negative 1/2 du. Nice and simple. So the antiderivative there is 2u to the 1/2, evaluated from 2 to 3. And that is 2 square roots of 3 minus 2 square roots of 2. And that doesn't simplify any further. What I meant to say on this particular example is this. Maybe I'll type The next example that we have is to find the integral from 0 to 1 of arctan x over 1 plus x squared dx. So now if I let u equal arctan x, du is 1 over 1 plus x squared dx. That ends up working out pretty nicely. So the integral of u du. Wow. Now all we have to do is change the bounds. So if x is equal to 0, u is equal to arctangent 0, which is saying when does tangent equal 0? Well, that is at 0. And x is 1, u is arctan 1, which says when does tangent equal 1? That occurs at the angle of pi quarters. So u is equal to pi quarters. So this becomes the integral from 0 to pi quarters. Super easy. The antiderivative of u is 1/2 u squared, 0 to pi quarters. So that will be 1/2 times pi over 4, the quantity squared, which will be pi squared over 32. This next one is a tricky u sub and a tricky formula. So this is an integral of the form, that formula was 1 over the square root of a squared minus u squared du, which gave you arc sine of u over a plus c. So in this case, if we let u equal just x squared, du is equal to 2x dx. So 1/2 du equals x dx. So we replace the x dx in the numerator. And we change our bounds. If x is 0, u is 0. And if x is root 2, u will equal 2. So this becomes the integral from 0 to 2. 1/2 du over square root 4 minus u squared. Factor off that 1/2. And then apply this formula. So the antiderivative of 1 over root of 4 minus u squared will be arc sine of u over 2. So that will be 1/2 arc sine of 1 minus 1/2 arc sine 0. And sine is 1 at pi halves. We have 1/2 times pi halves minus 1/2 times 0, which will give us pi quarters. And finally, a little bit of an application question. So water flows from the bottom of a storage tank at the rate R of t equals 250 minus 2t liters per minute, where t is between 0 and 120. Find the amount of water that flows from the tank during the first 60 minutes. So how much water leaked out? So if I find the integral 250 minus 2t, I want to find the area under this curve between 0 and 60. So I anti-differentiate, and that will give me how many liters leaked out. So 250's antiderivative is 250t minus t squared from 0 to 60, which is 15,000 minus 3,600 or 11,400 liters.